Hi, the SI meteorologist Paul Dorian here with a brief discussion on computer forecast models, equations, and input data. Well, one of the main forecasting tools used by a forecaster in today's world is the computer forecast model. The computer forecast models really became in vogue during the 1950s, but have evolved immensely over the last several decades, improved dramatically over the last several decades. Before the 1950s, there were no computer forecast models, and in fact there were no satellite imagery tools to use until about 1960, which is another reason why the forecast for the Normandy invasion, for example, during World War II was the most incredible forecast ever made, and of course the most pressure-packed, at a time when they did not have computer forecast models or satellite imagery to use as tools like we have today. Well, the main basics of a computer forecast model is input data in the form of surface observations and upper air observations, as well as satellite imagery, is used to feed into a computer forecast model, which then inputs the data in a series of fundamental equations that describe the atmosphere. And in these equations, time is one of the parameters, so it allows a prediction of some of the weather parameters such as temperatures and moisture. We'll take a quick look at some of these equations that are used in computer forecast models. And one of the things I want to point out here is this is a list of the equations that are used by the basic computer forecast model. And notice there's only a handful of equations. It's not like there's 50 equations or 100 equations. There's only several fundamental equations that are used to describe the atmosphere. To begin with, temperature and water vapor as a function of time is one of the equations, a couple of equations that are used in computer forecast models. Again, the fact that time is a parameter here allows a predictive state for temperatures and water vapor content. The equations of motion, of which there are three, help to account for horizontal and vertical motion in the atmosphere, and they factor in different forces like the pressure gradient force, Coriolis force, and friction, which all have an impact, for example, on wind speed and direction. Hydrostatic and continuity equation are two fundamental atmospheric equations that are utilized in computer forecast models. So again, all of these equations are used. Input data such as surface observations and upper air observations are fed into these models. It's cranked through these equations and output temperatures and moisture, for example, at different grid points in the future. And some of these models now go out to 15, 16 days. A GFS, Global Forecast System computer forecast model, goes out 384 hours or 16 days. And each one of these has some differences in the resolution of the models, both in the vertical and the horizontal, and the spacing between the grid points where the output parameters are displayed in graphical format. Now, one thing that any computer programmer knows is the output of a computer program is really only as good as the input. So I'd like to talk a couple of minutes about the input that's used for these computer forecast models, which are listed here below: surface observations, upper air obs, and satellite imagery. Well, first of all, here is a surface map with the surface reporting stations shown here on the Mid-Atlantic region in this case. And notice there's a fairly wide network, a dense network of surface observation reporting stations here. For example, Atlantic City, Philadelphia, Wilmington is hard to see here, but Reading is another one, Middletown, University Park, where Penn State is located, Du Bois, Altoona. These are all official surface observation weather stations that provide temperatures, wind speed and directions, and moisture at the surface that are utilized by the computer forecast models. Now notice there are some gaps in between these surface stations, and that's one of the inherent weaknesses of the surface observational network, as well as in a moment here we'll see even worse of a problem for the upper air network that we have. In fact, let's take a look at that right now. Here's a map of the Radisson network in the U.S. And this, again, these are reporting stations, official reporting stations that launch Radisson balloons that measure parameters like temperature and moisture from the surface all the way up to the middle or upper part of the atmosphere, depending on where the balloon bursts. And we do not have as dense of a network as we do down at the surface. Notice, for example, in the Mid-Atlantic region, we have only Upton, New York, Pittsburgh, Pennsylvania, Dulles Airport, and Wallops Island for the Mid-Atlantic region. So there's plenty of gap region in between these official upper air reporting stations. And the problem that these gaps cause is that small-scale weather features may not be captured by the surface observational network or the upper air observational network. Such things as sea breezes or small-scale isolated thunderstorms, for example, are certainly harder to detect when there are gaps in the reporting network. Now, why don't we make the network more dense? Well, budget reasons are main reason. One way around that, perhaps, especially in the near term or the midterm here, is to go to more and more satellite imagery. And in fact, we'll take a look at that right now. One of the advantages of satellite is, of course, it has a very wide view, and you can get a lot of information over a large area with just one or two satellite images. There are a couple different fundamental types of satellites I'd like to talk about. One is called the polar orbiter, and another is a geostationary satellite. The polar orbiter, listed here as the POSE, Polar Orbiter Environmental Satellite, is a type of satellite that moves across the world. It moves near the poles and may circle the Earth from the pole to the pole approximately 14 times per day. And the advantage of the polar orbiter is that it happens to move over and image data poor regions in our coverage. For example, radiosondes, very hard to get, of course, radiosonde data over the oceans and in some certain parts of the world, especially near the poles. So we now utilize polar imagery to infer temperatures and moisture, for example, in some of the data poor regions. And this information is fed into computer forecast models. Another type of satellite image is a geostationary satellite. GOES here, for example, by NOAA, from NOAA, is a geostationary environmental satellite that is fixed on a certain part of the world. Over the U.S., we have the GOES East, which is fixed at about 23,000 miles up, kilometers up. If GOES East is fixed on the eastern two-thirds of the U.S. and the western part of the Atlantic, whereas it GOES West covers the western two-thirds of the U.S. and the eastern part of the Pacific. The GOES satellite, the big advantage for the GOES satellite imagery is for short-term forecasters to use for such things as severe thunderstorm development, and of course, big advantage is to monitor tropical systems from the Atlantic that could move towards the U.S. So again, the surface observational network and the upper air observational network are now enhanced by polar orbiting satellites. And this may be a wave of the future where we get more and more from satellite imagery over the years to come. Here's in fact a trajectory of a Landsat satellite that is actually moving across this path. And again, it goes over some data poor regions that enhance our capability of utilizing data for computer forecast models. The SI has been involved with a lot of different satellite imagery projects over the years with NOAA and NASA and the U.S. military, ranging from NPOS to Landsat to GOES and to DMSP. And again, satellite imagery are being used more and more to infer temperatures and moisture in data poor regions. This website happens to be from the USGS. All you have to do is Google Earth now to see this particular polar orbiting type path that again is now headed for data poor ocean region, in this case the Pacific Ocean. Well, that is a description of how the fundamental equations used in computer forecast models and some of the input data that are used with the computer forecast models. And again, computer forecast models have improved dramatically over the years. What we could forecast 20, 30 years ago out 1 or 2 days, we can now forecast with the same kind of accuracy out 4 or 5 days, for example. And we expect computer forecast models to continue to improve over the next several years. That's it for now. I'm the SI meteorologist, Paul Dorian.